Welcome back. Today we're going to look at lesson 15. This will be the last lesson of this unit. Uh, Friday and Monday will be review days for us, and Tuesday will be the test. Remember to bring your Chromebooks to class. The test is online. And today we're going to look at comparing data sets some more. We've done this a little bit throughout the other lessons. So today we're going to do one last run of comparing data sets. Remember, a lot of this is going to be on your test, so we need to make sure you understand how to do this. So our learning target for today, by the end of the lesson, you should feel comfortable saying, I can compare and contrast situations using measures of center and measures of variability. So remember, my measures of center are my mean, which we use when we have symmetrical data, and median, which we use when we have non-symmetrical data. The measures of variability, when we have symmetrical data and we use mean, we can use mean absolute deviation, or more commonly, we can use standard deviation. And then when we use median, because we have non-symmetrical data, then we use the interquartile range. So as we look at today's lesson, the warm-up is called bowling partners. Should take about 10 minutes. And what's going to happen in this is it says each histogram shows the bowling scores for the last 25 games played by each person. They want you to choose 2 out of the 4 to join your bowling team. Now, this is one of those situations where there is no right or wrong answer. It's whether or not you can defend your choice, and if you can defend it using a measure of center and a measure of variability to explain why you want that person. Because there are reasons to pick all 4 of them. There's also reasons not to pick all 4 of them. So we're going to take 10 minutes. You can get in groups, talk amongst each other, and see if you can figure out first which 2 of the 4 would you pick, and then try to convince the other people around you that your choices are the best, and see if your group can come up with a consensus for which 2 they would pick. So if you're in class, go ahead and stop the video now. If you're watching from home, we'll go ahead and go over these. So as we look, we see person A. We have a mean and a median, and we have a standard deviation and an interquartile range. So if we look at this, they have a lower mean than maybe person B does, or even person C. But there's also a large variability. So while this person might score down here between 80 and 120, 130, there is the possibility that they could score all the way up to almost 200 points. So it just depends. Are you willing to risk the majority of the time this person scoring low for the possible reward that this person is every now and then going to pop out one of these games where they can bowl a 180, a 190? Now if we look at person B, this person is very consistent. They don't have any great games, nothing above 160. But they are very reliable. Whereas person A is going to have some games down here between 80 and 90 or 90 and 100. Person B is not going to bowl below 120. So it's a give and take. Am I willing to give up the possibility of 190 points so that I know I'm not going to get less than 120? That depends on how you want to strategize. If we look at the next two people, we've got person C. They have a high mean score, and it kind of centers around that, but they also had the lowest score overall. So while they typically will score 133, which is the highest mean available, every now and then they're going to bowl down here between 60 and 70. So are you willing to take that typical high score with the risk that every now and then they're going to have a really bad game? Or they could also occasionally have a really good game and bowl 210 to 220. So you have to weigh those odds. And then person D has the lowest typical score. But they also have two games where they almost bowled a perfect 300. So twice they were able to score between 290 and 300. And they are the only person that comes anywhere close to having a score like that. So you have to ask yourself, am I willing to take the lowest typical performance on the off chance that they might score 290 to 300, which is more than twice what anybody bowls typically? So there is no right or wrong answer to this question. This is a personal choice. The only thing right or wrong is, can you correctly compare the measures of center, meaning the mean and the median, and can you correctly compare the measures of variability, which are the IQR and the standard deviation? That's what you want to look like. And then it is a subjective argument, and it kind of comes down to who can make the best argument. Our next activity is titled Comparing Marathon Times, and this should take about 15 minutes. So in this one, it says all of the marathon runners from each of two different age groups have their finishing times represented in the dot plot. So my top dot plot are the runners between the ages of 30 to 39, and my bottom dot plot is measuring ages 40 to 49, and the numbers are representing the minutes that it took them. So if you think about it, 300 minutes is going to be 5 hours. 360 minutes is going to be 6 hours. So as we look at this, we're going to look at the shape, look at the variability, look at the measure of center, and we're going to answer these questions. So the first question asks, which age group tends to take longer to run the marathon? And explain your reasoning. So anytime we want to say which group tends to take longer, we're looking for a measure of center. So if we want to look at the measure of center here, we expect this measure of center to be somewhere around in here. And if I look here, my measure of center is probably somewhere around here. So the measure of center for the 40 to 49-year-olds is going to be farther to the right, meaning it takes longer. So maybe we say the 30 to 39-year-olds take, maybe 290 minutes or 300 minutes. Whereas we're saying the 40 to 49-year-olds, maybe they take around 340 minutes, 350 minutes, something like that. So the older group tends to take longer because their center is further to the right, and we're measuring time in minutes. The second question asks, which age group has more variable finish times? So if we compare, the fastest person in the 30 to 39 is looking to be around 230 minutes. The slowest person around 380. So they have an overall range of about 150 minutes, about 2.5 hours. But if we look at the 40 to 49-year-olds, they look like they go anywhere from the fastest at 250 minutes all the way to the slowest at 450 minutes. So that's about a 200-minute range, which is about 3 hours and 20 minutes. So the 40 to 49-year-olds have the more variable finish time because they are more spread out on the dot plot, and that's what variability talks about. How spread out are my dots on the dot plot? So as we look at the actual numbers on them, it asks what measure of center and measure of variability are most appropriate to use with the distributions. So if I was looking at this, when I look at these, I might say that these are skewed right because I have more of my dots down here on the left with a tail that stretches out to the right. And I kind of see the same thing down here. Most of my dots are down here 260 to 350, and then I've got a tail that goes out to the right. So if I was judging this to be skewed right, which means non-symmetrical, then I am going to use median and IQR. Because if I have non-symmetrical skewed data, I'm always going to want to use median because mean is affected more by those outliers. Next question asks, which points show values that are most likely to be outliers? So if we look at the age groups here, remember, outliers are anything more than 1.5 times the IQR above the Q3 or below the Q1. So this age group has an IQR of 65. 1.5 times that is right around 100. So anything below 160 and above 425 would be outliers. So if I look, I don't have anything down below 160. 425, I don't have any there. So we would not say there's any outliers in the 30 to 39-year-old range. Now if we look down here at the 40 to 49-year-olds, we've got an IQR of 92. If I take 1.5 times that, I'm adding 46. So that's 138. So if I had anything down around the 150 range, which I don't, so there's no outliers to the low end. And then we said 138, we add that onto here, so about 390, 425, 20. If anything was above about 520, it could be an outlier. And again, we don't see any there. So I would not say there's any outliers in either of these groups. And then it asks, based on the displayed information, are there any outliers? Mathematically, there are not. Everything is within 1.5 IQR of the Q1 and the Q3. Therefore, mathematically, there's no outliers. So our next activity is called comparing measures. This one should take about 15 minutes. And what they're going to do is they're going to give us different sets of dot plots, box plots, and descriptions. And for each group of data sets, they want us to determine the best measure of center and measure of variability to use based on the shape of the distribution. They want us to determine which set has the greatest measure of center, determine which set has the greatest measure of variability, and finally, make sure that you're able to explain your reasoning. So as we look at 1A and 1B, we have bimodal symmetrical, and we have bell-shaped symmetrical. So in this case, the mean and standard deviation are appropriate for these distributions because they are symmetric. The mean for distribution 1A is greater since the center is to the right of the center for distribution 1B. If you notice, the center here is at 8. The center here is at -10. And the standard deviation for distribution 1A is also greater because we have very few in the middle and most of our points out on the edges. But in B, we have most of our points in the center and very few of our points out at the edges. So 1A is going to have greater measure of center and the greater measure of variability. Now, if we look at 2A and 2B, we have what looks to be bell-shaped symmetrical and bell-shaped symmetrical. So again, we're going to use the mean and the standard deviation because we have symmetrical data. Then if we look, 2B has a center at 30, 2A has a center at 20, so 2B is the greater measure of center. And if we look at the variation, we go from 13 to 27, so that spreads out over 14. Here we go from 27 to 33, so that only spreads out over 6. So 2A is going to have our greater variability. Now we can look at 3. I seem to have skewed left data because the majority of my points are on the right. My tail goes to the left. 3B, I seem to have skewed right data because most of my points are on the left with my tail going to the right. Anytime I have skewed data, I'm going to use the median and the interquartile range. The median for distribution 3A is greater since the center is to the right of the center for distribution 3B. And the interquartile range is greater for distribution 3A since the data is more spread out in that distribution. Now we can look at 4. We have bell-shaped symmetrical for 4A. We have uniform symmetrical for 4B. If I have symmetrical data, I'm going to use the mean and the standard deviation. The mean in 4A is greater. It's going to be around 100. Here it's going to be around 89, 90. And the standard deviation for 4B is greater because the data is more spread out. It's even from one end to the other, where 4A has the dots concentrated mostly in the center. Now we can look at 5A and 5B. Here I seem to have skewed right data because my box is over here to the left. And in 5B, I seem to have skewed right data or skewed left data because my box is on the right and my tail goes to the left. So anytime I have skewed data, I'm going to use median and interquartile range. The median for 5A is greater than here. We can see that the median is this middle line. So the median is at 700. Whereas in 5B, the middle line tells us the median is 500. So the median is greater here in 5A. And if I want the variability, This box goes from 600 to 900, so that's a spread of 300. Here the box goes from 450 to 650, so that's only a spread of 200. So 5A would have the greater variability. Now they're going to give us descriptions instead of giving us a visual display. 6A says a political podcast has mostly reviews that either love the podcast or hate it. If you remember in class, I said the type of questions or the type of data that will get you bimodal is something that elicits an emotional response. And politics is probably the most popular. So if I have reviews that either love it or hate it, I'm going to have bimodal where my peaks are going to be on the ends. 6B is a cooking podcast, has reviews that neither hate nor love it. So people are kind of in the middle somewhere. So that is going to be more of a bell-shaped symmetrical with the dots centered in the middle. So now both of those would be symmetrical. So that tells me that I'm going to have mean and standard deviation because it's symmetrical data. And then if I have bimodal where my dots are out on the ends instead of bell shape where my dots are in the middle, the bimodal political podcast is going to have the larger variation. And then finally we have 7A, 7B, and 7C. 7A is a stress testing concrete. 12 samples, they all break at 450 pounds per square inch. So this is that dot plot where every single result is stacked right on top of the other. So it's symmetrical, so we're going to use mean and standard deviation. And it's not going to have any variation because every dot is on top of each other. 7B, samples break every 10 psi starting at 450 until the last one breaks at 560. So here we're going to have uniform data. They're going to break every 10 psi, so it's going to be the same all the way across. So my measure of center is going to be somewhere in the middle between 450 and 560, so that's roughly 505. And it's going to have huge variation because it's equally spread out all the way across. And then C only has 6 samples break at 430, and the other 6 break at 460. So in this case, my measure of center is going to be 445. So it will have the lowest measure of center at 445. Then 7A at 450, and then finally B at about 505. Variability, my uniform in 7B is going to have the greatest variability. My C, where I have some at 430 and others at 460, is going to be next. And then my zero variability is going to be 7A. And all of these that are described as being symmetrical, so we would use mean and standard deviation to come up with these. So when we're going through the questions, what were some ways you handled the last two problems? Well, you want to think about, if I did a dot plot, what would this look like? So we know that if the reviews are love or hate, I'm going to have bimodal. If the reviews don't love it or hate it, they're just in the middle, I've got bell-shaped. Every single sample breaks, I know I have that straight tower. Every sample breaks 10 psi apart, that's uniform. And then lastly, it only breaks in 2 different locations and they're equidistant apart. So what we can do is take the descriptions and in our minds start creating those dot plots, and then we can use any actual numbers they give us to come up with answers from there as well. So we figure out the shape first, and then we start looking at the numbers. How did you decide which data set showed greater variability? That would be determined either based off of the numbers, or you can actually just compare the shapes. So if my dot variability means how spread out are my dots on a dot plot. Well, if my dots are concentrated in the middle, I have low variability. If my dots are concentrated on the end, I have high variability. And if they're spread out over the whole thing like it's uniform, then I've kind of got this halfway variability. So that's how we can do it. We can look at the shapes and just compare the shapes. How do you compare the measures of variability for a data set? You're either using the standard deviation if it's symmetrical, or you're using the inner quartile range if it's skewed. The larger the number, the larger the variability. The smaller the number, the smaller the variability. How do you estimate variability when looking at data displays? You're looking to see which one has more dots or bars away from the center. So if they're close to the center, your high bars are in the center, that's low variability. If you've got bimodal where they're spread out on the ends and very few in the middle, that's high variability. How do you determine which measure of center to use for a data set? Measures of center are mean and median. If my data is symmetrical, I can use mean. If my data is skewed or non-symmetrical, I have to use median. Why is the median the preferred measure of center for skewed distributions? That's because if I have those outliers or the values that are high or low, my mean gets pulled towards the tail. So the mean changes more by extreme values than the median does. So we don't want to use the mean if I have skewed data. It's going to get pulled toward the tail and make my numbers wrong. And finally, why is the mean the preferred measure of center for symmetric distributions? If my data is symmetric, then my mean and my median will be approximately the same. The reason we use mean is because we actually do a calculation to find mean. We add them all together and divide by how many there are. The median is simply the middle number. So it's not going to be quite as accurate as the mean. That's why we use mean for symmetrical data. And our last thing is our cool down. Should only take about 5 minutes. You need to do this on Kitum. It's called Comparing Mascots. It says a new pet food company wants to sell their product online and use social media to promote themselves. To determine whether to use a dog or a cat as their mascot, they research the number of people who click on links with an image of a dog or a cat. And you can see the histograms right here along with the numbers. It says, based on the shape of the distributions, what measure of center and measure of variability would you use to compare the distributions? And they want you to explain your reasoning. And then the second question says, based on the data shown here, should the company use a dog or a cat mascot? And they want you to explain your reasoning. So that's the end of the lesson. Remember our vocabulary terms, our outlier. This is a data value that is unusual in that it differs quite a bit from the other values in the data set. Here they give you a visual display. They take the IQR, which is the size of the box. They multiply it by 1.5. The dotted lines show you that, and they show you where the fences are set up. So this fence is at 2.5. Anything less than 2.5 would be considered an outlier. This fence is at 42 and a half. Anything more than that would be considered an outlier. Standard deviation is a measure of the variability or spread of a distribution, calculated by a method similar to the method for calculating the mean absolute deviation. Remember, it starts out the same, but instead of just turning all my deviations positive, I square my deviations. Then I add them all together. Then I divide by how many there are. And my last step is to take the square root. And a statistic is any quantity that is calculated from sample data, such as the mean, median, or mean absolute deviation. So if you feel comfortable being able to say your learning target, I can compare and contrast situations using measures of center and measures of variability, then this lesson has been a success. If you still have questions about it, please ask me before the test on Tuesday so that I can clarify any misconceptions you might have. Thank you for the time watching this.